If you are following my videos for the preparation of NET examination, please like, share and subscribe. We now discuss the solution of a problem from the section Groups, and this question has appeared in the CSIR National Eligibility Test held in December 2023. The problem is related to the order of general linear group of 2 by 2 non-singular matrices with the entries coming from the quotient ring Z by 9Z. And this concept is completely new to the student who is a fresh postgraduate. And we know GL2, instead of Z by 9Z, if you have a field, finite field, then we know what is the order. And that is why it is beyond the comprehension of a fresh postgraduate. Anyway, let's now discuss this one in detail. And this question is from part C, which is a multiple select question. It can have more than one answer. It carries 4.75 marks and its question ID is 704085. The given question is, let G be the group under matrix multiplication of 2 by 2 invertible matrices with entries from Z by 9Z. Let A be the order of G. Which of the following statements are true? So we are given G is a group under matrix multiplication of 2 by 2 invertible matrices. That means 2 by 2 non-singular matrices or invertible matrices with entries coming from Z by 9Z, and Z by 9Z is isomorphic to Z9, and let A be the order of this group. Then which of the following statements are true? We are given four options. Option 1, A is divisible by 3 power 4. Option 2, A is divisible by 2 power 4. Option 3, A is not divisible by 48. And option 4, A is divisible by 3 power 6. So our concern is to find out what is the order of G. What is the order of G? So before going into the discussion of the problem, let us now recall the concept of GL2, ZP. What is this one? This one is, let G be the group of all 2 by 2 matrices ABCD, where ABCD belongs to the finite field ZP, addition modulo P, multiplication modulo P, where P is a prime number, it is a finite field, such that AD minus BC not equal to 0 under matrix multiplication. And this group G is denoted by GL2, ZP, where ZP is called a general linear group of 2 by 2 non-singular matrices over ZP. What is ZP? ZP is a finite field of order P, where P is a prime number. Then in that case, the order of GL2ZP is P square minus 1 into P square minus P. This we know. But now let us see the question, get into the question. Let us now discuss the solution of the problem in detail. We have the quotient ring Z by 9Z, which is isomorphic to Z9, and 9 is not a prime. And note that Z9 is not a field, it is a commutative ring with unity. Therefore, you cannot apply. So, given G is the group of 2 by 2 invertible matrices with entries from Z9 under matrix multiplication, that is GL 2 comma Z9. But 9 is not a prime. Therefore, you cannot make use of this formula. This formula will not work. Will not work. So, you have to now find the order of this one. That is the question. That itself is the question. And A is given to be modulus of GL2 comma Z9. Right. Right. Let's now discuss the workout of this problem in detail. Right. Consider GL2 comma Z9. What is this? It is a group of 2 by 2 invertible matrices under matrix multiplication with the entries coming from Z9. Z9. That is Z by 9Z isomorphic to Z9. And consider GL2 Z3, the group O under matrix multiplication of 2 by 2 invertible matrices with entries coming from Z3, where Z3 is a field, finite field with 3 elements, because 3 is prime. Note that Z3 is a field and Z9 is not a field and it is a commutative ring with unity. Now, we want to find the order of GL2 comma Z9. Now, we ask the question, get into when a matrix ABCD belongs to GL2 Z9. That means when a matrix ABCD where ABCD are elements of Z9 is invertible. Normally people think that AD minus BC not equal to 0. Not equal to 0 means AD minus BC modulo 9 is not equal to 0. Then it is invertible. Then it is invertible. Right. But you see, suppose you take 3003. Normally people think 3003 is invertible. It is not invertible. Why? Why? Because its determinant 3 3s are 9, which is 0. Which is modulo 9. 9 modulo 9 is 0. And its inverse does not exist. Then whatever, then A is equal to ABCD. When it is invertible, its determinant AD minus BC is a unit in Z9. That means if it has a multiplicative inverse, AD minus, that means determinant you take, and if it has a multiplicative inverse, that is a unit in Z9, then the matrix is invertible. Right. What are the units of Z9? The units of Z9 are, you see, 1, 2, 4, 5, 7, 8. What are the non-units? 0, 3, 6. They are not the units. So these are the units. Agreed. Now take A is ABCD belongs to GL2 Z9 is invertible. It means AD minus BC is a unit in Z9. That is AD minus BC. When you multiply the elements AD, BC, AD and BC. AD minus BC is an element which can spill over 9. Then you take the modulus, and that must be, because it is a determinant, it should be a unit, therefore it is congruent to U mod 9, where U is a unit belonging to the set of all units 1, 2, 4, 5, 7, 8. Let's now continue the next slide. So now we consider a map from GL2 Z9 to GL2 Z3 by phi of A, that is phi of the 2 by 2 matrix ABCD is pushed into A underscore, B underscore, C underscore, D underscore, where ABCD are elements of Z9 such that AD minus BC is congruent to U mod 9, where U is an unit. And what is the A bar? A underscore? A underscore is A mod 3. That is x underscore is x mod 3, b underscore is b mod 3, like that. The underscore denotes modulo, a underscore will denote a modulo 3. Now normally people think with this AD minus BC is a unit, it will work. Without this, people are talking, and this will not work, and it is not going to be a homomorphism. Not only that, it is not going to be a mapping at all. So some of the elements of GL to Z9 without will be pushed into the zero matrix of GL matrix, which is not an element of GL to Z3. That is why this condition that determinant AD minus BC is congruent to a unit modulo 9 is taken. Right. Now the question is, once again, sir, what is the guarantee that this A underscore, B underscore, C underscore, D underscore, this 2 by 2 matrix is an element of GL to Z3? Is it invertible? Is it invertible? Now, our first claim is phi of A, that means this is invertible. That means A bar D bar, that means A underscore D underscore minus C underscore B underscore is a not equal to 0 in GL to Z3, because Z3 is a field. So here now it works not equal to 0. So now A bar, A underscore is congruent to A mod 3, D underscore is congruent to D mod 3. Therefore, apply the properties of the congruences. A underscore D underscore is congruent to AD mod 3. Similarly, B underscore C underscore is congruent to BC mod 3, and apply again a property, that is A underscore D underscore minus B underscore C underscore is congruent to AD minus BC mod 3. Mod 3. What is AD minus BC? So that is equal to, is congruent to U mod 3. U mod 3. What is U? U is a unit. These are the units. Now take U is equal to 1. 1 mod 3, 1. U is 2. 2 mod 3, 2. U is 4. 4 mod 3 is 1. U is 5. 5 mod 3 is 2. 7 mod 3 is 1. 8 mod 3, 2. So what will be A underscore D underscore minus B underscore C underscore? It is either 1 or 2 in Z3. And where Z3 is a field, and that means this determinant, the determinant of phi of A is not equal to 0. Therefore, it is invertible. Because it is a field. Because it is a field. So, that's your definition of phi, is well defined, is proper. Right. Now, let's get into this, and we want to prove that phi is a homomorphism. Now, you take phi of AB, phi of A is ABCD, B is XYZW. That is equal to phi of matrix multiplication we have done here. And phi of this one is what? That is equal to, and that is equal to AX plus BZ mod 3, because, and AY plus BW mod 3, that is our definition of phi. CX plus DZ mod 3, CY plus DW mod 3. And now you can AX plus BZ mod 3 is A bar X bar plus B A underscore into X underscore plus B underscore multiplied by Z underscore is congruent to AX plus BZ mod 3. Therefore, replaced by their underscores. Right, this is a formula. Now, if you see this one, it is the product of two matrices A underscore B underscore C underscore D underscore multiplied by X underscore Y underscore Z underscore W underscore. What is this? Phi of A. What is this? Phi of B. So, phi of AB is equal to phi of A into phi of B for all AB belong to GL 2, Z9. Therefore, phi is a homomorphism. Good. Phi is a homomorphism. Right. Now, we want to prove that phi is a onto homomorphism. Most probably by this time you know what I am going to do. That is, I want to apply the first isomorphism theorem for groups. Right. So phi is onto. Phi is onto. So why? Note that every element of Z3 is also an element of Z9. Thereby, every matrix of GL2Z3 is also an element of GL2Z9. Right. So you take any matrix in GL2Z3, the same matrix will be there in GL2Z9. So therefore, if you take an element X in GL2Z3, its pre-image is the same X under phi, and thus phi is onto. So for every X belongs to GL2Z3, we have the same X in GL2Z9 such that phi of X is equal to X. And this shows that phi is onto. When phi is onto, so phi GL2Z9 to GL2Z3 is a homomorphism and it's a onto, it's a surjection. Therefore, apply the first isomorphism theorem for groups. That is, the domain group GL2Z9 by ker phi, that is the quotient group. The quotient group GL2Z9 by the ker phi is isomorphic to GL2Z3 because it is onto, it is the whole of GL2Z3. Now take the orders on both sides because they are all finite groups. So the order of GL2Z9 by ker phi is equal to order of GL2Z3. And the order of the quotient is order of GL2Z9 by order of ker phi because they are finite groups is equal to order of GL2Z3. That is, the order of GL2Z9 is equal to order of ker phi into order of GL2Z3. This is what we want, order of GL2Z9. Right. GL2Z3 order we know because Z3 is a field. Therefore, it is 3 square in minus 1 into 3 square minus 3. Recall this one. Right. So therefore, thus we got order of GL2Z9 is equal to order of ker phi into 3 square minus 1 into 3 square minus 3. Call is the capital 1 and we will utilize in the next slide. Right. What is that we want now? We want the order of ker phi. To find order of ker phi, first find ker phi. What is ker phi? The set of all those matrices from GL2Z9 such that phi of the image of that matrix is the identity matrix. So that means phi of ABCD is A underscore B underscore C underscore D underscore is equal to 1 0 0 1. And that is equal to A underscore is 1, B underscore is 0, C underscore is 0, D underscore is 1. What is A underscore? A mod 3. A mod 3 is 1, B mod 3 is 0, C mod 3 is 0, D mod 3 is 1. What is A mod 3 is 1? When A is 1, 1 mod 3 is 1. When A is 4, 4 mod 3 is 1. And if A is 7, 7 mod 3 is 1. So A mod 3 is 1 will tell you A is 147. B mod 3 is 0 will tell you B is 036. And C mod 3 is 0, 036. D mod 3 is 1, 147. So this is the set of all. A is equal to 147, B is 036, C is 036, D is 147. So A takes values 1473, B takes values 036, 3, C takes values 3, D takes 3 values. And you can check these are non-singular in the sense of GL2Z9. When you take their determinants, they will commit to be a unit. Right. What is the order of ker phi? The order of ker phi by the product rule of counting is A takes values 3 multiplied by B takes values 3 multiplied by C takes values 3 multiplied by D takes values 3. That is 3 to the power of 4. Order of care 5 is equal to 3 to the power of 5. We are done and we will go back to capital 1 and compute. And we have order of care 5 is 3 power 4 and we recall capital 1 equation. Order of GL to Z9 is order of care 5 into multiplied by 3 square minus 1 into 3 square minus 3. So the order of care 5 is 3 to the power of 4 into 3 square minus 1 is 8, 2 cube. 3 square minus 3 is 6, 2 into 3. So when you multiply, it is 2 power 4 into 3 power 5. So this is given to be A. We are given A is order of GL to Z9, that is equal to A is equal to 2 to the power of 4 into 3 to the power of 5. Let us recall our options. Now let's see option 1. A is divisible by 3 power 4. Yes. A is divisible by 3 power 4 because 3 power 5 is here. So 1. A is divisible by 3 power 4. Option 1 is true. Look at option 2. A is divisible by 2 power 4. Yes, it has 2 power 4. So A is divisible by 2 power 4. Option 2 is true. Right. And it talks about 48. Let us get into here. 2 power 4 is 16. 16 into 3, 48. Therefore, A is divisible by 48. But here it is given A is not divisible by 48. Therefore, option 3 is not true. Now, we see A is divisible by 48. But it is given A is not divisible by 48 in option 3. Therefore, option 3 is not true. And A is divisible by 3 power 5. 3 power 5 is the one, but we don't have 3 power 6 here. Therefore, A is not divisible by 3 power 6. So, and therefore, option 4 is also not true. Therefore, the answer to this question is option 1 and option 2. And that is the detailed discussion of the solution of the problem on the order of GL to Z9. And I have already told you that this is the beyond the comprehension of a fresh postgraduate. And it is, I rate it as very, very difficult question. Right. I am sure that you have understood the solution of this problem. And I wish you all the best. Thank you.